welcome to this deep dive
Yeah.
into the world of satellite safety algorithms.
Yeah.
It's
Right.
it's kind of a mind-bending thing to think about.
Sure.
But up there in that increasingly crowded space,
Mm-hmm.
we got to make sure those satellites aren't playing bumper cars up there.
Right.
You've given us some fascinating documents from Galaxity by Universe One,
Yeah.
and they're aiming to create a whole quantum satellite network, the outer net.
Right.
And these documents really delve into the algorithms behind how satellites avoid collisions.
Yeah, that's right. These algorithms are the brains behind autonomous collision avoidance systems, crunching numbers and making decisions to keep those satellites safe.
So imagine you're a satellite just cruising along in orbit.
Okay.
How do you even know if you're getting too close for comfort with another object?
It all starts with something called minimum separation distance.
Okay.
Basically, it's the space between you and another object measured in 3 dimensions.
Okay. So it's not just like measuring distance on a map.
That's
It's
right.
like figuring out how far apart two birds are, even if one is higher than the other.
Exactly. And to make things even more complex, we have to consider relative velocity.
Okay.
It's not just about how far apart things are, but how fast they're moving
Uh-huh.
and in what direction.
So two satellites could be pretty close,
Right.
but if they're moving in opposite directions, they might just zip past each other without a scratch.
Precisely. Think of it like 2 cars approaching an intersection.
Okay.
A head-on collision is a lot more dangerous than if they're just passing each other at a safe distance.
That's a helpful analogy.
Sure.
Okay, so we've got distance and velocity.
Right.
But even if two satellites are heading towards each other,
Mm-hmm.
there's still the question of timing, right?
Absolutely. That's where time to collision comes in.
Okay.
It's all about calculating how much time is left before a potential impact based on their current trajectories.
So picture this.
Okay.
There's this like time to collision clock ticking down in a satellite control room, and everyone's holding their breath.
Yeah.
Is that a bit dramatic?
It's maybe not quite that dramatic,
Okay.
but the time to collision is a critical factor that these algorithms use to determine the urgency of a potential collision.
Got it. So these algorithms are constantly monitoring the distance, speed, and direction of other objects,
Yes.
and then using those factors to figure out if a collision is actually going to happen.
Right.
And if it looks bad, they spring into action.
That's right. And the next layer of complexity comes in when we consider collision probability.
Okay.
It's not just about whether objects will collide, but how likely that collision is.
Hold on. So it's not just a yes or no.
Exactly.
It's a maybe.
Right.
How do you even calculate the odds of something like that?
Well, one important factor is something called positional uncertainty.
Okay.
Essentially, we can never know the exact location of a satellite. There's always a slight margin of error in our measurements.
So it's like trying to predict where a fly will land.
Yeah.
It's always buzzing around.
Right.
That seems like it would make things pretty difficult.
It does add a level of complexity.
Okay.
Because even if 2 satellites seem far apart, if there's a large margin of error in their positions, the chance of them bumping into each other goes up.
Okay. So even a small chance of a collision is still a risk.
Right.
Especially when you consider the potential damage and disruption it could cause.
Exactly. And this is where the satellite has to decide if it needs to take action.
Uh-huh.
That's where the autonomous decision threshold comes in.
Okay.
It's a dynamic formula that combines collision probability, the amount of change in velocity needed to avoid the collision,
Okay.
the time to collision, and even factors like how much fuel the satellite has left.
So it's not just about avoiding a fender bender.
Right.
It's about weighing the risks and benefits of taking action.
Right.
Like if a satellite blows all its fuel on a minor course correction,
Mm-hmm.
it might not be able to complete its mission.
You got it. It's a complex dance between safety and efficiency.
Okay, so the satellite has detected a potential threat,
Right.
assessed the risk,
Yeah.
and maybe even decided to take action.
Yeah.
But how does it actually figure out the best way to avoid a collision?
That's where the maneuver optimization cost comes in.
Okay.
It's about finding the most efficient way to stay safe
Mm-hmm.
while minimizing fuel consumption,
Okay.
time delays,
Uh-huh.
and even the computational effort involved in planning the maneuver.
So it's like finding the cheapest,
Yeah.
fastest, and least stressful way to get out of the way of a speeding car.
You could think of it that way.
Okay.
It's all about calculating the optimal path, even if there are multiple ways to avoid a collision.
So far, it sounds like these satellites are little mathematicians up there,
Right.
constantly crunching numbers and making life or death decisions.
Mhm.
But what about the actual process of avoiding a collision? Can we walk through what happens step by step?
Absolutely. It all starts with debris detection. Satellites use systems like radar and LiDAR, which is like a laser radar, to constantly scan their surroundings for potential threats.
So they've got their eyes peeled,
Right.
constantly looking for trouble.
Yeah.
But how do they tell the difference between a harmless piece of space junk and a real danger?
That's where the risk assessment comes in.
Okay.
Remember those formulas we talked about earlier, like collision probability
Yes.
and the autonomous decision threshold?
Uh-huh.
They play a key role in evaluating how serious a threat is.
Okay, so the satellite is constantly analyzing the data from its sensors,
Right.
comparing it to these thresholds,
Yes.
and deciding if it needs to take action.
Yeah.
It's like a continuous loop of observation and analysis.
Exactly. And if the risk assessment determines that a collision is like, the next step is maneuver planning.
Oh.
This is where the satellite calculates the most efficient way to avoid the collision.
And this is where we get into the nitty-gritty of how a satellite actually moves.
Right.
I remember seeing something in the documents about avoidance maneuver, delta V.
Mm-hmm.
What does that mean exactly?
Delta V is a measure of how much the satellite needs to change its velocity, both its speed and direction,
Okay.
to avoid the collision.
So it's not just about randomly swerving out of the way.
Right.
It's about calculating the precise change in speed and direction to get out of danger
Yeah.
while using as little fuel as possible.
Precisely. It's like playing a cosmic game of billiards,
Okay.
where you need to calculate the perfect angle and force to make the shot.
Uh-huh.
But instead of sinking a ball, you're trying to avoid a collision.
Okay, so the satellite has spotted a potential threat,
Right.
assessed the risk,
Mm-hmm.
planned its escape route,
Yeah.
and now it's time for the grand finale,
Okay.
the execution phase.
Right.
Is that where things get really tense?
Well, execution is certainly a critical moment.
Okay.
This is where the satellite uses its thrusters or other propulsion systems to actually change its speed and direction based on the planned maneuver.
So it's like the satellite is taking the wheel
Right.
and steering itself out of danger,
Mm-hmm.
but with all these calculations and maneuvers,
Right.
how do they make sure everything happens quickly enough? I mean,
Yeah.
space is big and things are moving fast.
That's a great question, and it leads us to one of the most exciting aspects of these systems,
Okay.
edge computing.
Edge computing. Okay, you're going to have to explain that one.
Sure.
Sounds like something out of a science fiction movie.
Imagine if your satellite had its own brain,
Okay.
capable of making decisions without needing to consult Earth.
Uh-huh.
That's essentially what edge computing is.
So instead of sending data back and forth to Earth,
Right.
which would take forever,
Yeah,
the satellite can just make decisions on the spot.
exactly. By processing information locally right on the satellite,
Mm-hmm.
we can drastically reduce what's called latency,
Okay.
the delay in communication.
Uh-huh.
And in a time-sensitive situation, like a potential collision, every millisecond counts.
So it's like having a supercomputer on board each satellite.
Right.
It can analyze data from its sensors,
Mm-hmm.
calculate risks,
Mm-hmm.
plan maneuvers,
Yeah.
and even execute those maneuvers, all without waiting for instructions from Earth.
Correct.
That's amazing.
It is truly remarkable how far technology has come.
Yeah.
These satellites are becoming more and more independent,
Mm-hmm.
capable of navigating the complexities of space on their own.
That's a lot to absorb.
Sure.
We've gone from measuring distances in space to talking about satellites with their own brains.
You're right.
Before we get too far ahead of ourselves, let's take a breath
Okay.
and recap what we've learned so far.
Sounds good. I think it's time to zoom out and look at the bigger picture.
Okay, so we've established that these satellites are essentially tiny, super smart spaceships
Right.
equipped with their own brains thanks to edge computing.
Mm-hmm.
They're constantly monitoring their surroundings, calculating risks,
Yes.
and planning maneuvers to avoid collisions.
Right.
But I'm curious, what happens after a satellite successfully executes an avoidance maneuver?
Sure.
Does it just go back to its original path?
It depends. Sometimes a single maneuver is enough to avert danger,
Go.
but in other cases, it might need to make further adjustments to ensure long-term safety.
So it's not always a one-and-done situation.
Right.
It's more like a constant dance,
Yeah,
adapting to the ever-changing space environment.
that's a great way to put it. These satellites are like vigilant guardians, always on the lookout for potential threats and ready to adjust their course as needed.
You know, it's
Yeah.
really fascinating to think about how much responsibility we're entrusting to these machines.
Right.
I mean, they're making life or death decisions up there.
Yeah.
With potentially millions of dollars worth of equipment at stake.
It is remarkable, isn't it? But this trend towards greater autonomy in space is driven by necessity.
Okay.
As we send more and more objects into orbit, managing them all from the ground becomes increasingly difficult.
It's like trying to herd 1,000 cats. Except the cats are hurtling through space at thousands of miles per hour.
Exactly. Autonomous systems are essential for handling routine tasks, monitoring for potential problems, and even making critical decisions in real time. This frees up human operators to focus on the bigger picture, the strategic planning, and scientific goals of the mission.
That makes sense.
Yeah,
But isn't there a risk in giving machines so much control?
sure.
What if something goes wrong? What if a satellite makes a bad decision?
It's a valid concern and one that engineers and scientists take very seriously.
Mhm.
These autonomous systems are designed with multiple layers of redundancy and safety checks
Hmm.
to minimize the risk of errors. Think of it like a safety net. If one system fails, there are backups in place to catch it.
Okay, that's reassuring.
Ah,
So it's not like we're just launching these satellites and hoping for the best.
right.
There's a lot of careful thought and planning that goes into making sure they can operate safely and reliably.
Absolutely. And as artificial intelligence continues to advance, these systems will become even more sophisticated and reliable, capable of handling increasingly complex situations.
Well, I have to admit, this whole conversation has made me think about the future of space exploration
Yeah.
in a whole new light.
Yeah.
It's not just about humans venturing out into the cosmos.
Right.
It's about creating intelligent machines that can help us explore and understand the universe in ways we never thought possible.
I agree. And these collision avoidance systems are just the tip of the iceberg when it comes to satellite autonomy.
Okay.
The same algorithms that keep satellites from crashing into each other can be adapted for a wide range of tasks.
Really? Like what? I'm picturing a satellite doing my taxes while it orbits the Earth.
Maybe not taxes,
Okay.
but they can definitely help with things like optimizing fuel consumption, which is crucial for extending the lifespan of a mission,
Uh-huh.
or coordinating complex maneuvers for satellite formations.
Satellite formations, what are those? Sounds like something out of a Star Wars movie.
Imagine a group of satellites working together,
Okay.
like a synchronized swimming team,
Mm-hmm.
to achieve a common goal.
Okay.
They might be used for things like Earth observation,
Huh.
creating communication networks,
Mhm.
or even conducting scientific research.
So instead of having a bunch of individual satellites doing their own thing,
Right.
you have a coordinated team working together.
Exactly.
That sounds incredibly efficient.
It is, but it requires sophisticated algorithms to ensure the satellites maintain their formation,
Mm-hmm.
adjust their positions as needed, and of course avoid collisions with each other and other objects in space.
Okay, I'm starting to see the bigger picture here. These algorithms aren't just about safety.
Right.
They're about expanding our capabilities and allowing us to do more in space than ever before. It's like having a whole team of robotic explorers at our disposal.
Exactly. And as the space industry continues to grow, we can expect to see even more innovative applications of these technologies, pushing the boundaries of what's possible in space exploration.
Speaking of pushing boundaries, the documents you shared mentioned something about orbital debris density estimation.
Okay.
What is that and why is it important?
That's a great question. As we launch more and more objects into space, the amount of debris in orbit is growing rapidly. This debris can range in size from tiny flecks of paint to defunct satellites, and it poses a significant risk to operational spacecraft.
So it's like a giant cosmic junkyard up there, and we're
Right.
just adding to it with every launch.
In a way, yes. And that's where debris density estimation comes in.
Okay.
It's about using statistical models and observational data to assess the concentration of debris in different regions of space.
So it's like creating a map of the most cluttered areas so satellites can avoid those high-risk zones.
Exactly. By understanding where the debris is most concentrated, we can plan safer trajectories for satellites and reduce the likelihood of collisions.
But I imagine it's a pretty complex calculation, right?
Yeah.
Space is vast, and those pieces of debris are constantly moving. It seems like it would be impossible to keep track of everything.
It's definitely challenging, but scientists and engineers have developed sophisticated models and algorithms to track these objects and estimate their distribution.
Okay.
They use data from ground-based radar systems,
Mm-hmm.
optical telescopes,
Uh-huh.
and even space-based sensors to monitor the movements of debris and predict its future trajectory.
So it's like a giant game of cosmic hide and seek,
Right.
but with potentially catastrophic consequences if we don't find those pieces of debris in time.
That's a good analogy.
Yeah.
And the challenge is only going to increase as we launch more and more objects into orbit.
Okay. That's a bit worrying.
Mhm.
What steps are being taken to mitigate the risks posed by space debris?
Sure.
Are we just going to keep launching things until we have a full-blown space junk crisis?
Thankfully, there's growing awareness of the problem, and several initiatives are underway to address it.
Okay.
Some organizations are developing technologies to capture and remove debris from orbit.
So it's like having a giant cosmic vacuum cleaner sucking up all the junk?
Well, it's a bit more complicated than that, but the goal is to actively remove debris from orbit. Other organizations are working on guidelines and best practices to encourage responsible space operations.
So it's a two-pronged approach.
Right.
Cleaning up the mess we've already made
Yeah,
and preventing future clutter.
exactly. And those efforts are crucial for ensuring the long-term sustainability of space exploration. We need to find a balance between utilizing space for our needs and preserving it for future generations.
That makes a lot of sense.
Yeah.
We wouldn't want to turn space into an unusable junkyard.
Right.
So we've talked a lot about the technical aspects of satellite safety and autonomy,
Uh-huh.
but I'm curious to hear your perspective on the bigger picture.
Okay.
What are some of the ethical considerations that come into play as we develop these increasingly intelligent systems?
That's an important question. As we give machines more and more autonomy, we need to think carefully about the potential consequences.
Okay.
One concern is the potential for bias in algorithms.
Bias. How could an algorithm be biased? Isn't it just a set of instructions?
Well, algorithms are created by humans, and humans have biases.
Uh-huh.
Those biases can inadvertently be encoded into algorithms, leading to unintended consequences.
Uh-huh.
For example, an algorithm designed to identify potential collision threats could be more sensitive to objects of a certain size or shape,
Okay.
potentially overlooking other threats.
So it's like having a security guard who's really good at spotting tall, skinny people,
Yeah,
but completely misses the short, stocky ones.
that's a good analogy.
Yeah.
And it highlights the importance of carefully testing and evaluating algorithms to identify and mitigate potential biases. We need to ensure that these systems are fair, reliable, and accountable for their decisions.
It sounds like there's a lot to consider here.
Sure.
It's not just about the technology itself, it's about the ethical implications of how we use it.
Exactly. As we develop increasingly sophisticated autonomous systems, we need to engage in open and honest conversations about the potential risks and benefits, and work together to create a future where these technologies are used responsibly and ethically.
Well said. So it seems like with every step forward in technology,
Right.
we're also presented with new challenges and questions to grapple with.
Yeah,
It's both exciting and a little daunting at the same time.
I agree. But I'm optimistic that we can rise to the challenge. The same human ingenuity that has led to these incredible technological advancements can also help us navigate the ethical complexities they bring.
Well, on that note of cautious optimism, let's take a quick break. When we come back, I want to explore some of the potential applications of these satellite safety algorithms here on Earth. Welcome back. We've been talking about satellites dodging space debris
Right.
and making decisions on their own up there.
Yeah.
But it's occurred to me that this technology might not just be for outer space.
You're right. The principles behind these algorithms, sensing the environment, predicting movement, making decisions, these have applications much closer to home.
So the same smarts that keep a satellite from smashing into space junk
Right.
could be used to prevent,
Yeah.
say, a self-driving car from running a red light.
Exactly. In fact, the development of autonomous vehicles is already drawing heavily on the principles and collision avoidance and path planning that were pioneered in the space industry.
It's mind-blowing to think that the technology that's guiding satellites millions of miles away could one day be keeping us safe on our daily commute.
It's a great example of how advancements in one field can have a ripple effect, leading to innovations in seemingly unrelated areas.
So besides self-driving cars, what other earthly applications can you envision for this technology?
The possibilities are vast. Imagine using these algorithms to optimize air traffic control,
Okay.
preventing collisions and reducing delays, or coordinating the movement of drones in complex environments like disaster relief zones.
So instead of a sky full of near misses,
Right.
we'd have a perfectly choreographed ballet of drones delivering aid precisely where it's needed.
Precisely. And even in manufacturing, these algorithms could guide robots to work alongside humans with greater safety and efficiency.
It's like having a team of incredibly precise, tireless assistants, always aware of their surroundings and never making a wrong move.
Exactly. And as these technologies continue to evolve, we can expect to see even more creative and impactful applications emerge, blurring the lines between the digital world and the physical world.
It's a future full of potential, but also one that requires careful consideration.
Right.
We've already touched on the ethical aspects of autonomous systems,
Mm-hmm.
and it seems like those concerns become even more pronounced when we bring this technology down to Earth.
Absolutely. Transparency, accountability, and fairness need to be at the forefront of our minds as we integrate these systems into our daily lives.
It's a reminder that technological progress isn't just about creating new gadgets and systems. It's also about understanding their impact on society and shaping a future that benefits everyone.
Well said. It's a shared responsibility that requires collaboration between scientists, engineers, policymakers, and the public.
Well, I think we've covered a lot of ground today for the
Mhm.
technical intricacies of satellite safety algorithms to their potential to transform life here on Earth. It's been a fascinating journey, and I have to say I'm leaving with a sense of awe and a healthy dose of curiosity about what the future holds.
Me too. It's an exciting time to be alive, witnessing the rapid evolution of technology and its power to shape our world.
And to our listeners, we hope you've enjoyed this deep dive into the world of satellite safety and autonomy. It's a topic that's both complex and captivating, and we encourage you to explore it further. Who knows, maybe you'll be the one to come up with the next groundbreaking application of these incredible algorithms.
The sky's the limit, quite literally.
Until next time, keep looking up and keep wondering.